So, welcome back after lunch. Now we're going to hear about formal methods at input-output. Can you clarify, is it now input-output global or Hong Kong?
Yes, so
what's the branding like these days?
We're going through a rebranding exercise at the moment.
Okay.
So, yeah.
Anyway, so applying formal methods to the Cardano blockchain. Take it away.
Thank you. So, hello, I'm James Chapman. I'm head of formal methods at IO. So I'm going to talk to you about applying continuous formal methods, which is the name of our formal methods strategy, to Cardano, the blockchain. So the paper is joint work between me and so I'm a formal methods person, and Arnaud, who's an architect, and also a very hands-on architect. So he's also kind of he's also a developer as well. And Polina, who's a formal methods person, but also she's worked in research. And all three of us have a research background. So I think we're sort of covering sort of engineering, research, and formal methods, and how to kind of integrate those here. And of course, I should say that this is based on joint work with a great many people, all of the engineers within IO, the rest of the formal methods team, and the researchers. And yes, and two of my colleagues, Kevin Hammond and Luther, are here. So if you would like to talk to them, feel free. So I'm going to, just to give some context, I'm going to say a little bit about the company, about Cardano, our approach, the continuous formal methods approach, and about how we've applied it to the Cardano node. That's the software that people are running on the internet to support the network. And so I'm going to give some case studies there, and also how we apply it in innovation R&D, so bridging the gap between research and development. And then, as this is an experience report, I'm going to reflect a bit on the challenges we face, and how we meet those challenges, and also how we've kind of refined our approach. And then at the end, I would like to advertise a couple of things. Okay, so I'm going to start with the company. So input-output. So we are a blockchain R&D company. We were founded in 2015. We have about 500 people. We have quite a big research department and research connections. The high-level ones, I think, really are with Edinburgh, Stanford, and Tokyo Tech. But we have lots of other kind of direct and very effective research collaborations with groups or with individuals. So we have quite a big lots of research connections, and we put a lot of work into research. So we've written around about 200 papers. We're also kind of a big part of or we support the functional programming community. So we support the Haskell Foundation. We've been involved from an early stage with that. We support JFP. We are sponsoring types. We have a booth if you'd like to come and talk to us outside, and we also sponsor other academic events such as Types and the Agda Implementers meeting. And we are the company that built the Cardano blockchain. So let me say a bit about Cardano. So to me, the aim of Cardano is to be the world's financial operating system. And actually, in an earlier talk, there was a reference to which made me think about this. There was a reference to the Little Typer book, and I reviewed that book. I think my name is somewhere in one of the early pages, so I hope I'm not de-anonymizing myself. But I reviewed it, and MIT Press kindly sent me a rather small fee for the work, and they sent it to me as a check in US dollars. So it took quite a while to arrive in Glasgow, and then I haven't had a check for a while, so I kind of thought, I've got to go to the bank, and then I went to the bank and it was shut, and then a couple of weeks later I managed to go to the bank and it was open. And first of all, they tried to send me away, and because they tried to get you to do things on your phone instead of actually going into the bank. So I got through that, and I gave them my check, and they looked a bit puzzled, but I thought it's from MIT Press, and it looks like a very recognizable US bank. I thought they should be able to deal with it, but it took a very long time, and a month and a bit had passed, and then they sent me a message saying that it wasn't the kind of standard check, and I was thinking, I think it's quite a well-known bank, but anyway, eventually I got my small fee converted into pounds and into my bank account after they'd taken a rather large fee, and it took several months. So I think this is a nice example why it'd be nicer to have a world financial operating system. And also having got mortgages in 2 countries, I think having these kind of some financial history which is transferable would also be useful. Anyway, moving on back to Cardano. So Cardano is the number 11 cryptocurrency by market capitalization. It has a daily volume of around about $200 million US. These are some figures I looked up the other day. It's really rooted in research. So one of the foundational things is the Ouroboros consensus algorithm. And as I said, we've written a lot of papers, and as I go through my talk, I will sort of highlight connections with papers or where we've written papers about what we're doing, or papers have been an input into what we've done and how we've done it. It's written in Haskell and formalized in Agda. This is a little bit of an oversimplification, but I think it's reasonable. Of course, there are specialist bits that are written in languages other than Haskell to do with cryptography, and there are other things that we do beyond Agda. It's proof of stake, so it doesn't use enormous amounts of electricity like Bitcoin, and it's based, as I said, on the Ouroboros consensus algorithm, which has really been a competitive advantage, and is something that has had widespread adoption in other blockchain systems. And that's some research that is centered in Edinburgh. It's built by IO, and I've missed somebody off here, so so it's built by IO, and we work closely with Twig, Well-Typed, Galois, and Cuvic. I should have put Cuvic on, so apologies, John. So yeah, so we have so I think we're really, we have an excellent team, and we also work with the kind of best of breed consultancies, specialist consultancies in the Haskell ecosystem. It's decentralized, and it becomes more decentralized over time. So in the very beginning, the kind of block production of the system was federated. So there was only a small number of entities which could generate blocks, and then a big step was really decentralizing the block production, and we have these so-called SPOs, which are called stake pool operators, and that's a bit like a miner in the Bitcoin terminology. And these are people who really are running businesses that on top of Cardano, they've built their businesses, and they're all over the world, and there are hundreds and thousands of them who are doing that. So they're the ones who are responsible for block production, because an individual, maybe you don't want to have a computer running all the time. So what you do is you delegate the right to do that to these stake pool operators. They take care of having some infrastructure, and then they distribute the rewards. And this is all happens automatically. You don't have to lock the currency, and it works very well. And then the next step in terms of decentralization is decentralizing the governance, so people can make decisions about how the system is going to develop and that kind of thing. And that's something that's happening right now. So this functionality has been rolled out, and at the moment they're having 50 workshops around the world to get input from the community, and then they will have a ratified constitution soon, and that will progress. So decentralization is a big focus. Right, now on to formal methods and how we use it. So let me just say a little bit about the formal methods team so you get a bit of a picture. And we had a reviewer comment who was wondering about the kind of size of the team. So I thought should mention this. Formal methods team is not enormous in IO. We have 11 specialists. We do have some open positions. And we have a kind of bigger group of people within the company who are interested in formal methods. So, I mean, we have about sort of 20 people who regularly attend our meetings. And of course, we work with other people in the teams as well. So the default model that we try to follow is to have formal methods engineers embedded in the teams. We don't want to be a separate entity doing different things. We want people to be in the team, providing value to the team, and it should be really part of the process. We are kind of spread across the company, not terribly evenly, but yeah. So that's something that I think will increase over time. So we work on the Cardano node, on smart contracts, on Midnight, which is a different project, on JED, which is a stable coin running on Cardano, and in R&D, so bridging the gap between research and development. And as we work in those projects, we really have sort of two priorities. One is in R&D, we're really focused on bridging that gap, taking something from research, getting it ready to be implemented. And then on the engineering side, we're kind of, as I said, we're working with the team, and we're trying to provide that extra level of high assurance, and also to accelerate future development. So to put people in a position where their code is trusted and is well understood, and then they can, if they're considering changing something, they can, they know that feel safe about what they, the system they've got. There aren't any kind of hidden gotchas, and they can examine the trade-offs and things. So that's the kind of position we want to put engineering teams in. Oops. So let me say, so I've put this on a red slide. It's green on there, which is confusing. Okay, but yeah, a different coloured slide. So this is the strategy we adopt. We try to get involved in an early stage, so ideally at the research stage. We develop formal artifacts that can grow and change with the project. So that means they can't be too heavy, or they shouldn't be too light. So we want things that are adaptable, and we can, as we work with the team, we can kind of tune what we're doing. And we also have to tune the level of formality to the project. Different projects, we can do different things. So some things are easier to apply than others, some things are more important, so we have to be adaptable. And a key thing, this is really the continuous part, is that we want to lock formal methods into the development workflow via continuous integration and testing. So we don't want it to be a separate document in a separate repository that somebody has to change the code and go, oh dear, I haven't updated the specification, and then they drift over time. And this, so by doing that, we keep things in sync, and it also forces us to be able to go as fast as the engineering team, and I think it enforces a lot of good qualities the same way as it does for integration and testing. And another key thing is that we want to be involved at the late stages of development. So we don't want to be like an intervention. We want to be involved at the late stages of development because that shows that the approach is working. But the main thing is, as I said, it puts people in that position where they've got, they know how their code works, and they trust it, and then they can move forward from there. So rather than, let's say, they consider a new thing, then they have to go back to the very beginning and model it from scratch. So that's really the aim. And I think getting to that point where you can make those changes with confidence is really important to the health of a project. So rather than kind of like, you become a victim of your own success and you don't dare change things, I think it's good to be in that position where you can be agile. So I'm going to talk a bit about the Cardano node. It's very confusing, my slides are green because it's all white and red on my screen. Okay. So the Cardano node is the software that runs on the stake pool operators and other users are running on the network. And this is a live system, right? So, this is really about changing, it's a bit like changing the tires while the car is driving. So making changes to this and introducing new things. So the high level architecture of this is that we have we try to, as much as possible to have a pure core and then sort of isolate the complicated stuff. So in the middle, we have the smart contract layer, and the smart contract approach in Cardano is based on a very simple fundamental. So a smart contract is really like a kind of a decision procedure that can just say whether or not it's a sort of custom decision procedure about whether you can spend some money. So it's like a sort of custom lock. So it's quite a simple model. But when you connect this with tokens, and we have native tokens, then this gives you quite a powerful model. But that's very simple. It's just a decision procedure, just a function that says yes or no. And then the ledger rules are also quite simple. That's just a simple, it's a simple state machine. So, the state is the kind of current state of people's wallets or everybody's wallet, and the current state of the money that's held in the treasury. And then the transaction is the input to that state machine. And then if it's a valid transaction, then you go to a new state. So that's quite a simple concept, and it's amendable to formalization. Consensus is the next layer, so that's sort of not really interested in what's in the blocks. It's interested in maintaining a block tree of all the different chains, which may include forks that people are communicating. So it's maintaining that tree. It's determining which is the best one, and it has to kind of track that information. And then you have the networking layer, and that's about maintaining connections with the other peers and sending, being asked to send a message, asking for more information. So this means that you can put the kind of the I/O and the concurrency stuff into the outside here, and you keep the core simple, as simple as possible. And then you have the node, which kind of ties this all together. So I think a pure core has been a big part of the design approach here, and also this idea of designing for testing and verification, designed to make those things easy. I'll say a little bit more of that in practice about how that's applied to use for testing things like disk I/O and other things. So I think that, having that going into this process with that in mind has been a big thing. And also, when it comes to verification, having these simplified, this sort of simple core where the ledger, for example, isn't, the code isn't polluted by things to do with consensus or I/O. I think that's very helpful. So let me say a bit about the smart contracts. So the smart contract system, the surface language is called Plutus TX, and it's basically like a subset of Haskell. So people can write their code in Haskell, and it's compiled to a low-level language called Plutus Core, which is not actually that low level. It's actually based on lambda calculus. So it's based on system F omega mu, and in fact, the types are actually erased in the last step. So really what's running on the blockchain is really untyped lambda calculus with some extra primitives for things like cryptography and byte strings and other things. So it's quite a conceptually simple language. And the idea was to keep that as simple as possible and something that's well understood, because backward compatibility with blockchain is a massive thing. You still have to be able to run all the contracts that people wrote in the past. So maintainability is key. And they have this system of having a sort of stable language but the built-ins are things that might change. So you might swap out a hash algorithm, put in a new one or something like that. But the idea is the main language stays the same. We have an AGDA specification for this, which is kind of like a language specification. And this first paper, System F and AGDA Fun and Profit, is about that. So it's intrinsically typed and scoped, which makes illegal states unrepresentable, which is a term that was mentioned earlier today. We have a reference implementation of that evaluator and a reference implementation of the type checker. So this is in AGDA, but you can compile it to Haskell and run it. And in principle, you could just take it and plug it in to the production system, but we use it for testing. And then there's another piece of work. So this is something that has come. So the first paper is something that we kind of developed as a team. The second paper is where IO has funded research at Utrecht, and Jaco, Manuel, and Gabriel and Wouter have worked on translation certification. So this is this grey box idea to compiler verification or certification. So at each stage, the compiler can output the intermediate language that it's working on, and then you can then separately check if it's preserving the meaning of the program. So you get a certificate for a specific program rather than a sort of CompCert-like from scratch certified compiler. And that's something, so that work is something that we recently put into practice. So that's used now on the untyped optimization passes in the production toolchain, because that's somewhere where there's more risk, because having the types earlier on actually catches a lot of problems. So that was a sort of area, right, this is where we need to do some extra stuff. And as I said, this reference implementation is used for conformance testing, so we can generate an arbitrary Plutus contract and we can run it on the production evaluator or the reference one, and we can see if they give the same answer. Yes, this AGDA-generated certification code is actually in the production tooling. I would like to get, in the future, to the point where we have verified code in the node, but this is an important step where we have it in the tooling. Here's a little example so this is the evaluator. This is the CEK machine. It's a bit of the CEK machine. So this is intrinsically typed, takes something in a state T, a state of type T to a state of type T. So if it's a variable, you look it up. If it's a lambda, then it's already a value, and you change modes. If it's an application, you stash the argument, and you carry on processing the function. If it's a type function, it's a value, so you change modes. If it's a type application, you stash the type argument and keep processing the function. And so these are for the recursive type, so you kind of go inside these things. If it's a constant, then that's a value change modes. And this is the rule for if it's a an unapplied built-in function, so we just consider that a value. There's some more complicated things you need to do when you actually apply a built-in function. And then we have an error code which stops evaluation. And this is, so that would be something like divide by 0, or where you verify signature and it doesn't verify, that kind of thing. So that's intrinsically typed. Okay, so let me say a bit about so that was sort of the first case study. Let me say a bit about the ledger. So the ledger has gone through various iterations. So the system has gone through various iterations, and the ledger has evolved at that time. So the Byron system is this federated system, and they had a big separation of the spec and the implementation. So the spec was kind of retrospective as a way of understanding the code, but it was written in LaTeX and mathematical notation, so that really gave a good understanding of the problem, but it wasn't very well connected with the code, and people were not terribly happy with the code at that time. So then they tried something new for the next step. So in the Shelley era, this is when they made the system decentralized, and they had these stateful operators. Then they had an upfront specification in LaTeX. They wrote a reference implementation, which became a victim of its own success and became the production implementation, which you can think of as a good thing or a bad thing. So they kind of had a rewrite of the system. There's still a problem, though, in that this gap develops because they were under pressure. I mean, the engineers are always under pressure, and then the specification and the code diverge. You implement optimizations in the real implementation, and then it's harder to see if this matches up. And at the same time, they also wanted to do better with the testing. So they used to generate whole kind of blockchains to test, but people still worry about, I think there was another nice comment about, being paranoid is a good plan. So I think it was put rather better on the slide, but anyway. So it's good to be paranoid. So they were worried about the coverage of their testing approach, so they wanted to do better. In the Alonso era, that's where they introduced smart contracts. So here we have the extended UTXO model. So that was a kind of separate research effort to kind of develop the functionality in a simplified way, with a kind of paper and a prototype and a formalization, and then that was then applied later. So that was really where we kind of, that was a piece of research which fed in. And then in Conway, so that's the new era where they have governance, then they've evolved the approach. So now, to avoid having this gap, they have an AGDA specification instead of a LaTeX one. So that can generate a PDF that people can read, and it can also generate Haskell code, which you can use for testing. And they have a new approach to testing, and this is something where they work very closely with Cubic, and it's about generating states. So not generating whole chains, so they can generate states, and then they can explore particular interesting areas, and also do more advanced testing where they can mix randomized testing with certain places that they want to get to. So I think people are much happier with the testing, and that's been a big advance, and also closing that gap. So as I said, that's used for conformance testing. We also have a paper which talks about this AGDA approach to the ledger specification, which was at FMBC, I think. And this UTXO paper was, I can't remember where it was now. Okay. Here's a bit of a flavor of a rule from the ledger. Rather annoyingly, this rule is actually about checking the script, but this seems to be where the state gets updated. So the system is a kind of hierarchical state machine, where there's a different state machine for checking different things, and it all fits together. So there's another rule where it actually checks the things, but this is where the state is updated, and this is what I really wanted. So this stuff along the top is the kind of above the line is checking stuff about that the scripts are valid, but here, you go from a state S via a transaction, and then, a transaction has inputs and outputs. So the inputs are the things you're spending, the outputs are the things that are being produced. So you have to subtract the inputs from the UTXO set, which is the money that hasn't been spent, and then you have to add on these new outputs, which is the new things that can be spent. So that's that update. And then a transaction, you have to pay some fees, which goes into a central pot, so that has to be updated. And there's also some deposits you have to make to stop people making lots of tiny transactions to slow things down. And also you can donate to the treasury if you want, so that capability is there as well. But that gives you an idea, and this is very similar to how you would write it in LaTeX, but this can be turned into a function that can be run. And we have a tactic that turns functional relations into functions that we use. So that gives us a kind of nice middle ground. In consensus, so this is a more challenging area. So they've used the type system to enforce things, and Simon Peyton-Jones said at ICFP the other day that I think that the type system is the most, is the most well-used formal method. So this is where they've really tried to use the type system as much as they can. And they've also gone through a process as the algorithm has been developed. So these are based on peer-reviewed papers written by our research department, and this team has also evolved their testing approach. So they used to test by simulating a whole network of interacting nodes, and now they prefer to test having a single node and then within an environment. So the environment would represent how it's talking to the network, and they find that more effective. And at the same time, we've also recently introduced an AGDA specification, and we did this by going to talk to the team and saying, what are your biggest concerns? How can we help? And they said, well, the block header processing, which is quite a simple thing, so is something that we would really like to have a formal spec for. So that was the first thing that we did. So yes, so that's kind of like, it's a bit, so the blocks are split into the bodies, which the ledger people care about, and the headers, which the consensus people care about. And this was a place they were keen to have something. So that's what we've started with there. And this is a rule. I'm not going to go into details, but it's sort of, you can see it's similar in style to the ledger rule. It uses the same framework, which we can reuse. And here, you have a state, which is some certificates and some nonces, some random numbers, and a pointer to an earlier block. And then when you process a new block header, if it's okay, then you update all these things. So it's the same kind of approach. In networking, they also have used the type system extensively. They have kind of mini protocols, and then they encode these in the type system, so the code can't do things that are not allowed by the protocol. We've done a lot of performance modeling, particularly of block diffusion, which I think I have on my next slide. So to think about how long it takes for the whole network to get a block. The networking layer is very reliable. We have very good uptime with our system. And it runs on the public internet by individuals, so it's a decentralized distributed system. So this is a big success. And this area also uses kind of mock testing, so they can simulate disk access or disk errors and concurrency and cryptography by using IOSIM. And that means they can actually, the production code is parameterized over these kinds of activities, as I said, concurrency and disk access. So they can they can test and use in production the same code. So that's very nice. And this is a paper which is about the performance modeling. And here's an example of this. So what we want to achieve is that all of the nodes in the network get the next block in 5 seconds with 95% probability. And then you can think about, well, how big can we make the blocks? Or if we wanted the block to be a certain size, how fast does the network want to be? We want the network to be all over the world, right? So you can, my point is, here it is. So if you sort of read up from 5 seconds, you can see that a lot of these things are too big. So we're kind of in that region of 64K, 256K are okay, but the other things are too big. Right, so that was the Cardano node. So let me say a bit more about R&D. So this is kind of a different emphasis. So this is about research driving engineering. So what we want that to be a smooth, effective process. So I really like this definition of innovation. So invention is a flower and innovation is a weed. Right, so it's really about adoption. It doesn't matter if you have the world's best idea, if it's not just going to kind of grow on its own. So, and this is from Robert Metcalf, who I think he invented Ethernet at Xerox PARC, and but to get adoption, he founded his own company, and he put a huge effort into into sales, into talking to customers, finding out their problems, and I think that's the thing. It's not just, the idea, he already had the idea, but it was really that effort and focus on innovation that made it a success. Going back to our innovation process, so in R&D, we're focused on taking these, well-chosen ideas from research, and which we follow a software readiness level system, which is a bit like NASA's TRL system. So a research idea is kind of SRL1, and a system in production is SRL9. So we're trying to get things from 1 to sort of about 6, say. So that's kind of like within a 4, 5, and 6 are kind of like, you've really explored the area well, you know all the trade-offs and things, but it's in a kind of laboratory environment. So you might think with something that's got to work in space, at some point you might be just kind of testing it underwater. So that would be a realistic level. So that would be somewhere in 5 or 6, I think. And the idea is we want to take these ideas from research, and then we want to get them to a point where they can be implemented by a production team, even outsourced. So we'd like to get to the point where we know exactly what we want, and we have the mechanisms to be able to judge if something is built externally, whether it meets the specification. So we want to go through that process in about 6 to 12 months. We have an interdisciplinary team. We have all the relevant people working together. So we have the kind of basic templates. We have a researcher, a full methods engineer, sometimes a cryptographic engineer if it's relevant, a product expert, an architect, and a prototyping engineer. Changes a bit. Sometimes we don't have one of the roles. Sometimes we double up. We tend to have researchers and product experts split between multiple projects, but that's the kind of basic template. And we also work with the research team on the other side, and with the engineering team on the other side, and with the community. So we want to, we want to do that communication as well. So here's a couple of examples. So I have 2 examples of R&D projects. So this is Ouroboros Peras. This is the next iteration of the consensus algorithm, which is aimed at fast settlement. So this is about speeding up the settlement, which is probabilistic, and it's kind of the way I imagine the UI is a bit like when I make a bank transfer, and it says, well, this might take 2 hours, or it might take 1 day, and then 5 minutes later it says, oh, your money has already been sent. So this kind of gives you that earlier settlement, which is very valuable. This is one of 4 consensus projects that we are currently working on. We're working closely with the researchers, so we have a sort of good feedback loop with the researchers. The innovation team has given feedback to the researchers, which has changed their design, and the paper is something that they're planning to submit soon. We have a relational form model, and this is sort of based on approaches that are similar to some work by Baz Spitters and Ilya Sergey on how to formalize safety and liveness for consensus protocols. We experimented with a monadic DSL for the cryptographic pseudocode, which is how the researchers write their protocols. So we want to also work with the researchers. We'd like to have a common language to do that. So that's something that we've experimented with in this project, and we plan to do more on. We're using QuickCheck Dynamic in Agda, so it's compiled to Haskell with Agda 2HS. So that's a state machine testing approach developed by John Hughes and others at QVic, and that's about, as I mentioned before, it's about exploring the state space, but where you have key areas that you want to explore. We also have a Haskell prototype, so we can use that, so we can conformance test that and test it generally using QuickCheck. And we've also done this performance modeling because it changes things about the blocks, and also this approach introduces votes, because the way it works is people can vote on blocks, and that's how you get the faster settlement, because you take that into account as well. And we have something called a SIP, which is a bit like an RFC. This is how we work with the community, and this is an example. So this is actually the SIP here. You can see we have there are 5 authors which are all in these different categories of, so we have architect, prototyping engineer, researcher, formal methods engineer, and a product person. So we have that, they're all part of that design. This document is actually a liter agda file, so it has also bits of the model in there, bits of as the specification. So that's something like an RFC that we want to get discussion, and that's a kind of a document which explains how this has been explored. And this is at sort of SRL 4. And this is the development process model that they follow in which is rather complex. We have some other ones which are simpler, but this is very interesting because it has has 3 areas really. There's the research paper on the left. There's the AGDA specification where we have the specification and the test model. So we're not sort of doing conformance testing there. It's kind of like there's a soundness argument. And then this is compiled to Haskell, and you can run a Haskell prototype. You can also run things such as a Rust prototype against this system. So this is how they do it. So there you go. And on the research side, they have this pseudocode, and then also we want these safeness and safety and liveness theorems. Let me say a little bit about another one, Babel fees. So this is about where you might want to pay for a transaction on a chain A with tokens from a chain B. So you don't, maybe you don't even know you're using blockchain. You don't know what the underlying currency is. You want to pay in some other currency. Then this is a system where you can sort of offer, well, I would like to pay in this currency, and maybe you can be matched with somebody who is willing to pay your fees in ADA, in our case on Cardano, and would take what you're offering in return, or maybe they're kind of they're presenting a service where they're going to pay all the fees. That's another model. So this is really, so the previous project, the Paris project, is really aimed at changing the consensus protocol. This one is more really a change to the ledger. And we have a formal model for that, which builds on this AGDA model for the ledger. So that's showing that by being involved in at a late stage, we can build on things we've already got. So that's really like a direct PR to the ledger formalization. And we also have a Haskell prototype, which is a PR to the Haskell implementation. And this is so there was a research paper about this previously by my colleagues, and now we have a SIP that's ready for discussion with the community. So just a little glimpse of that is one of the changes is changing the transaction body to allow also for you to be able to say, well, I'm going to fulfill, I'm going to pay some extra, essentially, I'm going to fulfill some demand, or I might say, well, there's something missing here, I'm requesting that somebody else provide that. So that's this sort of extra change, and this is some Haskell code in this case from the SIP. Okay, so that was kind of the overview, the case studies. So let me say a bit about, so kind of reflect a bit on the approach and also the challenges of applying formal methods. And this has sort of partly come out of a discussion with my co-authors. One of the reasons we're having this discussion, that was one of the reasons we decided to write this paper. And this also reminds me of so there's a very nice experience report in the last session of ICFP by Pedro from Standard Chartered. He sort of called some of these myths. So some of them, it's a problem. It comes down to interpretation, I think, in some ways. So one of the potential challenges with formal methods is how can you integrate it with development practices and also kind of with the tooling. So one of the things, so Arnaud, my colleague, he's a really big fan of kind of pair programming, mob programming. He would sort of like to block off the afternoon in his calendar every day to work with his colleagues on a technical challenge. But that relies on everybody kind of you need to be quite a homogeneous team to do that. And this also sort of ties in with this agile, if you take the kind of textbook agile approach where the idea is that you have all these different tickets or stories, and really anybody in the team can take them on. So the other side is that you might want to have an interdisciplinary team, or you want to have specialists in different areas. So these things, you have to find a balance there. But there is, inevitably, if you have somebody working in a team who's responsible for one area, you do have, that comes with, that changes the way things work. So that's inevitable. And also the development practices, the kind of the tooling, you want to be able to think, I think we have a good argument for that because we have things tied into CI. But yeah, so these do pose challenges. Yep, 5 minutes. Okay, I better get a move on. So there is also, it's a specialism for methods in the same way as functional programming is. So there are fewer people, and it was interesting that Pedro said he actually finds it easier because then it kind of narrows the search, looking for people who have this expertise, and they are better than the average. So I think that's an interesting point. But it is a specialism. There are fewer people. Also, we tend, particularly in R&D, we're using kind of researchy, prototypey tools. So these are immature. They break. We have to contribute to them, that kind of thing. So we do have those problems. And then this sort of contributes to having specialists and maybe have sort of siloing. So you have to work to make sure these things don't happen. So these are these kinds of the challenges. So I can say how we address those. So one of the things we put a lot of effort into is knowledge sharing. So between the 4 methods engineers working on different things, we have seminars, and we like to share information, work with other team members on the team. So we don't really have this complete divide. We have people kind of in the middle who can do some things. So that's knowledge sharing. Upskilling. So that's about teaching engineers about 4 methods. So for example, we had an AGDA course taught by Phil Wadler last summer, or was it this? I think it was last summer. And we invited engineers, so we trained them in the tools. So engineers, I should say, and researchers. So we trained them in the tools, and they're now on video. So new people who join the company can then watch those lectures. And we've also had I personally, several years ago, I had a similar experience going and learning about Quick Check, which John Hughes taught, which was one of the things, when we were thinking about this AGDA course, was one of the things that I had in mind, because that was where John's company really taught all of the engineers in the company how to do property-based testing, and I think that was fantastic. I think another key thing is having a common language. So I mean that in 2 ways. We actually would like to, when it comes to working with the researchers, I'd like to have a DSL for the pseudocode, but at the same time, the other element of that is also just kind of understanding what everybody else is doing. So we need to learn a bit of research. The researchers need to learn a bit of kind of what happens in R&D. The engineers need to learn about R&D and research. So, we need to kind of expand to get a common language and greater understanding. And we also want to involve researchers at an early stage in the development, and also really involve formal methods engineers and prototyping engineers in an earlier stage. So we don't want to have a kind of wait till the researchers are finished, then we do R&D, then it's passed over to the engineers. We want to have a much more integrated approach with fast feedback loops. And also expanding reach into other areas we haven't looked at yet, and improving the tooling. So, that's always a big factor, and I think that's a big cost saving. It's often a kind of hidden cost, is people waiting for CI or having issues with tooling. Have I used all my time? Oh dear. So, I think we've also refined the approach that we use, the strategy. So we try to get involved in an early stage, but we want some level of stability. We would like to have a kind of draft research paper. We don't want something that's changing all the time, or we don't want to do loads of proofs about something that's constantly changing. So we have to kind of wait a little bit and judge, how big a start to make at what point. And we want to develop formal artifacts that grow and change. One thing that works quite well is having a small, simplified end-to-end example, which we then add detail to later. So that works quite well, rather than kind of looking at a small area. We have to tune the level of formality to the project, and partly that's sort of knowing when to add detail or add proofs, for example. But also we have this balance between standardized tooling or customizing things to the project. So you have to find the balance there. We want to lock formal methods in. That's really important, but an early, very useful thing is just having a type check spec. So that's really useful. And as I said, we want to stay involved to the late stage. I'm not refining that. I think that's important. And there we go. I'm on my last slide. So we are hiring. We have 3 open positions. We're looking for interns. And I also wanted to advertise some other work, which is about consensus algorithms, which is outside of Cardano. Thank you.
All right, so while you guys set up, we can maybe do 1 or 2 questions. You go ahead.
Hello, hi. Really nice talk. So I have one question. In one of the slides, you mentioned that you extract out the ACTA specification to a PDF.
Pardon? Sorry?
Sorry, in one of the slides, you mentioned that you extract out the ACTA specifications to a PDF.
Yes.
So is that in a natural language style or is it still in the...
It's in a kind of mathematical notation. So
Okay.
we started off having kind of LaTeX, set theory mathematical notation, and we want to kind of stick to that. So
Okay.
we used to write that manually, now we have kind of ACTA that generates something as close as possible.
Okay, so it's not exactly in the ACTA style, but it's more understandable because it's mathematical.
So it's mathematical. So
Okay.
it's really cool to, our researchers and engineers who are happy with that.
Okay, that's pretty cool. Yep, thank you. Yeah.
As we segue, thank you again, James.